Hello and welcome to the Daily Space for July 2nd, 2018. My name is Dr. Pamela Gay and I am here to try and put a little bit of science into your brain. It is clearly a Monday, but Monday or not, the science must go on. So let's switch over to today's top story. This is one that I was able to read some of the highlights on last week and was extraordinarily happy to get to bring to you this week. We have new results, not that you can tell from this artist's rendition, but astronomers have finally been able to detect the light being emitted in the area of space around where two neutron stars merged, that we could see them last August. This is one of those stories that's kind of hard to discuss because when something occurred and when we detected it are extraordinarily different due to differences in, how long it took the light to get here. So a distant gamma ray burst went kapooey. It was, in this particular case, the merger of two neutron stars. So gamma ray bursts come in two different flavors. Those that are triggered by hypernova that we can see for a fairly long period of time. And these events are just giant stars that go boom in the night or the day. Depends on where in the world you are. Now, the other kind of gamma ray burst remained much more elusive to try and observe the afterglow of because they last for only brief moments. Luckily, with this particular short gamma ray burst, we were able to see it not just with our gamma ray detectors, but we also got optical afterglow detections of it, and it was detectable by the LIGO system. These are giant facilities that shoot lasers down an L-shaped arm of detectors. And what happens is, as the lasers come back, shoot out and come back, they create an interference pattern on a detector. And if the length of the arms, either one of them, changes ever so slightly, this can get detected as a change in the way the light appears on the detector. With a neutron star merger, we get waves of gravitational energy flowing across, our cosmos. And these appear as a contraction and then re-expansion of our universe, or at least our local part of it, as the gravitational wave goes by. Back in August, we detected the gravitational wave, the gamma ray burst, the optical afterglow, and the object promptly went behind the sun. This is one of those problems with astronomy. We can only see things that are on our side of the sun. So this particular amazingly interesting object hasn't been observed for about 110 days. Now that the Earth has moved, we are able to see the region of space this object is located in, and astronomers peering at it with a variety of telescopes have picked up the optical afterglow. So 110 days later, and the press release that I'm looking at is coming from Warwick University. They were using the Hubble Space Telescope to do these observations. And using the Hubble Space Telescope, they picked up the optical afterglow. They no longer see evidence of nuclear reactions going on, such as was seen directly after the merger of the two neutron stars took place. Instead, we're seeing the normal growing nebula that surrounds, supernova and weirdo reactions like this. So, welcome to the brave new world of understanding short period gamma ray bursts and knowing where gold comes from and knowing that gravitational waves periodically crunch your body a little bit smaller and let it expand a little bit back out. Now, moving on to slightly easier to understand science, this is an actual image. This was one that when I looked at it, curse words came out of my mouth. Now, they were ones of joy, not sorrow. And it's because of what we're able to see in this image. This perfect circle of black in the center of the image is created by, well, an obstructing mask that is being used to block the light from a dwarf star. The surrounding image, and this is an image taken with the Very Large Telescope. It's actually not ALMA this time. This is an infrared image. And what we're seeing is the dust disk around the dwarf star and a newly formed gas giant. This bright glow is, well, it's a baby star. It's a giant baby star. And this is one of our first confirmations of seeing a star independent of seeing a planet independent of its star. So we've been able to image planets' spectra as they pass in front of a star. We've been able to see starlight dimming as a planet passed in front of the star. We have, in a few cases, detected older planets that had escaped their star somewhat. This image is claiming to be the first confirmed image of a newborn planet caught with the European Southern Observatory's Very Large Telescope. Now, there's a lot of caveats on that. So it's the first detected with the Very Large Telescope. But the reason and the first newborn, and the reason that they have these two caveats is because ALMA, the Atacama Large Millimeter Array, also located in Chile, has been imaging the dynamical effects, the gravitational tugs and pulls on gas disks that are created by planets forming inside those gas disks. So with all these caveats, they know they're right. And between ALMA and VLT, we now have a new era opening to us of being able to capture these amazing snapshots of solar systems in the process of forming. One of the ways that we're able to understand astronomy is by looking out across space and taking images of the same kinds of objects that are at a myriad of different ages. This is perhaps easiest done with star clusters, where on a nice fall night you can go outside and see stars still forming in the Orion Nebula. You can look over to the Pleiades and see an open cluster that is in the process of ending its planetary formation. You can then look over at the eye of Taurus the Bull and see around it the Hyades cluster, which is an older open cluster in the process of falling apart. By studying each of these very differently aged systems, we're able to get snapshots of what star clusters look like as they form. We can't, because human beings are short-lived, ever get to actually watch this entire process take place. But because the universe has, well, babies and senior citizens around when it comes to stars, we're able to capture all the different ages, the same way you might see all the different ages of a human being at a family reunion. Now, with the VLT and ALMA capturing these amazing images of, well, planets in their various stages of formation, we're going to, for the first time ever, be able to say, this is what a planet looks like just as it starts to form out of the disk. This is what a planet looks like as it finishes wiping its orbit clear. We're building up a movie, one star system at a time, of the evolution of planets as stars begin to turn on and light up the sky. This is kind of an amazing point to be watching what's going on, and it's amazing for a couple of different reasons. 20 years ago, people would have told you we require space-based telescopes like the Hubble Space Telescope in order to make this kind of super high-resolution image, but Hubble couldn't have done this. It couldn't have done it for a variety of different reasons, ranging from it just didn't have quite the same detectors to, well, it didn't have a big enough mirror to go quite this faint, and it certainly didn't have the right kind of coronagraph to block out the light from the central star. This image was taken from the top of a mountain here on the planet Earth, where astronomers can go out and add new instrumentation, well, as often as their funding allows them to build it. No spacecraft launch required. Now that we're able to use multimeter and many multimeter telescopes from the surface of our planet with adaptive optics to essentially erase the effects of our atmosphere, we're able to do things that we once thought could only be done from space. Now, this isn't to say we don't still need space telescopes. We need a spacecraft like James Webb Space Telescope to get up off the surface of the planet and go orbit somewhere else so that they can see the colors of light that just don't make it to the surface of our world. We are restricted in what we can see because our atmosphere does reflect and absorb certain colors. Now, by getting better at what we can do from the planet, we free our resources to focus on just those colors that we can't see from the planet, allowing more science to be done for less dollars, which, well, means more science to be done. Now, continuing our adventure in search of planets, the Japanese are launching a new instrument on the ground. Once again, we are starting to see data coming in from a new ground-based telescope program. In this case, we're looking at the Subaru telescope in Hawaii, where they have mounted an instrument capable of searching for planets in a way that we haven't been able to do quite before. Some of you may remember that back in the mid-90s, the first way we were detecting planets around regular stars was by looking for the spectral lines in a star to slightly shift from the red to the blue and back again as a planet went around and around a star, causing the star to move ever so slightly due to the gravitational pull of the planet. This back and forth movement of the star moves the star towards us, shifting its light to the blue, and moves it away from us, shifting the light to the red. In order to measure these very slight changes, because these stars are moving slower than, well, those fire trucks that race past your house. These tugs and these related color shifts are measured in comparison to often just a cell of gas that is placed in the spectrograph instrument that generates its own comparison lines that the starlight can be compared to. Now, this isn't always ideal. You run into lots of problems with calibrations. You have to get everything just right. It works consistently, but this is perhaps best described as fiddly. Now the Japanese are working on developing something that, instead of requiring us to get our cells of gas set up exactly right, illuminated exactly right, and providing us comparisons only at the wavelengths the gas has, well, absorption and emission lines. What they're doing instead is using a laser to pulse out comparison lines on their CCD. And what they're doing is they're measuring the shifts in the wavelengths of light compared to the pulsed laser light. In this image, you can see there are the dashed lines of the laser next to the mostly solid, but with some dark spots where atoms in the starlight have absorbed the light that is being emitted deeper down in the star. By looking to see how these absorption lines shift next to the dashed laser light, they can get very, very precise measurements of stellar movements, allowing us to, well, see planets we might never have been able to detect before. So here we go. Basically, one step at a time, uncovering where are all the planets. The next question is going to be the great Fermi paradox of, with so many worlds out there being discovered, where are all the aliens? Well, currently we don't have any instrumentation to help us answer that question, but time will tell. We are slowly but surely confining the variables in the Drake equation, that equation that describes the probability of life existing on other worlds. Next up, in fine-tuning all of the variables, is coming to understand how likely it is for life to evolve on other planets. What was once a philosophical way of trying to understand things is starting to become a measured way of understanding things. Once again, to explain how this new way of planet formation works, astronomers are pulsing a laser on the CCD, marking out specific pixels, specific places, and then comparing the placement of the laser pulses to the actual stellar spectra. The atoms in the star absorb light out at very specific wavelengths. These wavelengths are determined by what are the atoms in the atmosphere of the star. Every specific atom only absorbs light in certain colors that correspond to the energy differences between different electron energy shells in the atom. Some of you may remember from high school chemistry when we had to learn the atomic shells of various atoms, that S1, S2, sets of shells, and the energies that, well, corresponded to them. As each atom absorbs light at its own specific wavelength, this provides us markers of how fast the star is moving towards us or away from us, because we know these atomic fingerprints will have specific spacings. If we see a specific spacing, it probably requires more than 2 lines, and we see this entire set of very specific spacings get shifted one way or the other. That shift is going to be related to the star moving towards us or away from us. By measuring those shifts, we can keep everything understandable. I mean, that's a strange way to put it. By measuring how much everything is shifted, we can see how fast the star is moving towards us, away from us, and we know that those short period tugs are caused by a planet. This is complicated, but doable. And it's that doable that is going to lead to even more planets being discovered. Now, to look at my favorite former planet, this is Ceres. A lot of people are very anxious to see Pluto reinstated as a planet, but do you know it is not the only former planet in our solar system? Ceres is the biggest of the asteroids, and once upon a time in the 1800s, people, well, thought it was a planet. Once we started finding asteroids in vast numbers, it was realized, we either have hundreds to thousands of planets, or we need to rename these pieces of rock to be something else. So Ceres, which is round like a world, which has its own amazing geology, is now just called a space rock or an asteroid scientifically. Well, in order to help understand this and other space rocks, NASA launched the Dawn space mission many years ago to go on a journey to visit first Vesta, which is in the inner part of the asteroid belt where things are warmer and got baked dry, and then to fly out further and visit Ceres, which is beyond our solar system's waterline, which means it got to keep its moisture. Well, when we first got there, we realized this was a world unlike anything we expected to find. And that realization continues to be re-emphasized on a nearly daily basis. This image that I'm showing you was taken while the Dawn spacecraft was located a little bit more than 30 kilometers above the surface of Ceres. And you can see this beautiful, slightly cratered surface up at the top regular part. And then this is the edge of a crater. And you can see these amazing rocky outcroppings. And you can see evidence of landslides going down the edge of the crater. Now, this isn't any everyday crater. This is actually this amazing crater that you see in the pullout image down here in the left. And as you may have seen in the news several years ago, Ceres has these unexpected bright spots down here in this crater. And these bright spots, they aren't just this weird facet of illumination angle. They are seen from all angles, and they are seen over time. Well, now that the Dawn mission is a whole lot closer down to Dawn's surface, working on a highly elliptical orbit that allows it to get these amazing close-ups, we are starting to get increasingly detailed views of just what those, well, weird white spots are. In this composite image, you can see that there is this strange icy plateau deep in this crater. This icy plateau actually has the substances dripping down the sides. It is now understood that this is briny water, salty water coming out from somewhere in the interior of Ceres through a process called cryovolcanism. This is ice being extruded out through volcano-like objects. They geophysically act like volcanoes, but instead of spitting out lava, they spit out, in this case, salt water. In addition, we're also seeing the dried up shiny reflections of sodium carbonate. Now, you may remember that when we first started talking about these bright spots, there were people who were like, oh my gosh, that's ice. This thing has water that is getting spit out. And then we also have people who are like, nah, it's just salt. Well, it turns out both groups were right. There is salty water being ejected through the surface of Ceres, through the cryovolcanism. And this salty water is building up shiny salts on the surface of Ceres. Sometimes there's just one answer, and sometimes everyone is right. You're right, you're right. All the scientists are right today as we get this amazing new image of Ceres. Now, that was today's news highlights. This is the Daily Space. As it says over my head, I am Dr. Pamela Gay, and I am here to put science in your brains. The show is brought to you by CosmoQuest. Join us at CosmoQuest.org, where we invite you to help us explore our solar system. Help us build maps of the craters and other features on our moon, Mars, Mercury, Vesta. And once we finish Vesta, we can start in on Ceres. Check it all out, and please help us make a science. The CosmoQuest project is a collaboration of multiple institutions that is run out of the Astronomical Society of the Pacific. We're working in collaboration with folks like Dr. Matt Richardson at the Planetary Science, Annie Wilson at Youngstown State University, who you may have seen on this channel yesterday. At the ASP, you have me, Big J, and of course, Dr. Andreas Plazas. You can find us every Monday through Friday, bringing you the daily space at 1 p.m. Eastern, 6 p.m. London, 10 a.m. Pacific. Wednesdays and Fridays, we follow up with an Astro 101 course taught by Dr. Matt, although this Wednesday I expect him to be out celebrating the American 4th of July. We also have all sorts of other projects. For instance, I come on Tuesday nights and work on doing data visualizations, and Annie comes on for Sunday Science to show you just how it is that planetarium shows are constructed and all those amazing images you see are made. If you like what you see, give us a follow. Follows are free and we'll let you know whenever we go live with new content. If you want to sustain our efforts, every subscription really helps and every bit matters. So drop me your questions in the chat, and if you would, please at me so they're easier to find. So scanning, and Fenrig has the first question of the day about the absorption line measurements. Is each laser pulse of different wavelength, or is something else there being compared? Now, the way that we get spectra, let me go back to showing you that image. The way that we get spectra is we take the light and we spread it out using a prism, a diffraction grating, some sort of a mechanism that spreads the light out according to wavelength. What we have in this particular image is, and I'm going to try and zoom this image out so you can see even more of it. So what we have in this particular image is the light has then been folded up so that we have across each line its own segment of the rainbow. Now, the spectrum varies things according to what color it is. But the CCD itself doesn't care. The CCD itself is like, either I have light or I don't care which. And so the CCD doesn't care what color the laser light is. And other instruments are used to spread the laser light out into pulses that match the spectra but don't have the same color as the spectra. Let me see if I can figure out a better way to put this. So they're calling this instrument the infrared Doppler, and the way they describe it in their press release is they've created a laser frequency comb that provides a standard ruler for measuring the line of sight movement of a nearby star to within a few meters per second. They don't actually answer your question. So let me see if, since they didn't provide a better explanation, I can provide a better explanation. Essentially, they're pulsing the laser, and it sounds like they're moving the laser in order, so they're pulsing it, and then they're not retuning it, but they're actually moving it. Thank you for the follow, Obi-Wan Kenobi. I need a prop. Okay, let's pretend that this barrette is the laser. So the laser is pulsing light. Now they're only trying to measure changes of a few meters per second. So they have their laser and they're pulsing how often the laser light is. Now, as they're pulsing it, they're changing the velocity of the laser. And as they change the velocity, they're moving the laser, this ever so slightly changes the color of the laser light. So they have very precise measurements because they're pulsing it. That creates the size of the dots, and they have very precise measurements because they know how fast it's moving and what its core velocity is, what its core color is. So with this combined information of what is the actual wavelength of the laser at a given pixel, what is the thickness, because they know how fast the pulse was, and what is the original color of the laser. So you start with the original color, you then use the velocity, you get the apparent wavelength, which is what's measured on this. You use the apparent wavelength then to get at what is the color being seen from the star. So yes, they're moving the laser. You don't have to move it very fast because the stars aren't moving very fast. That Doppler shifts the laser light, so they're not retuning it. Lasers aren't something you can generally retune, and they're getting these comparison pulses. I hope I was finally able to answer that question. It's a complex instrument. You have to have all the moving pieces moving just right. And with spectrographs like this instrument isn't actually mounted onto the telescope. Generally, the light is taken from the telescope and funneled through something like a fiber optic cable, and then the light that has passed through the fiber optic enters an instrument that may be filling the basement underneath your telescope. These are room-sized instruments that are used to spread out the light and very carefully make measurements like this. This is where it really starts to matter. Are there any light leaks? Do you have all of your instrumentation maintained at a constant temperature? All of these things go into play, and these massive structures, and I don't know why chat needed to reset when I sorry about that. I reopened Streamlabs. Chat is still there, I believe. Yes, there we go. Yes, close the expletive door. One of the strange things that we have had to deal with is OSHA regulations here in the United States that say if the power goes off, emergency lights are supposed to turn on. Except if we're in the process of taking an extraordinarily long exposure, you don't want emergency lights to turn on. So quite often you'll go to an observatory and see many of the lights unplugged. Theoretically, they all get plugged back in when people are working in those rooms. So let me switch back to the host view and go to looking to see what other questions you guys have for me. Scrolling. I'm glad I was finally able to answer your question, Fenring. Are there any other questions out there? So Peter, I don't know if there's organics on Ceres. Salts are made out of sodium atoms versus out of carbon atoms, and it's carbon atoms that really get used to define something as being organic. So it's not the biggest mountain in the solar system on Vesta. It may just be the saltiest mountain. The biggest mountain in our solar system, that record is still held by Olympus Mons on Mars, where you have that perfect combination of lower gravity than Earth, which allows the volcano to build up to be much taller, and past volcanism that allowed the volcanism to exist. So Obi-Wan Kenobi is asking, could Pluto regain its status as a planet? And I'm going to add to that, could Ceres? Because, hey, I'm Team Ceres. Yeah, it's totally possible. That I know of, we aren't actually voting on that matter this year at the International Astronomical Union meeting in August. And what it would take is a new definition that allows anything that fits a specific geological definition to be defined as a planet. Right now, we have a definition that actually is quite troubled in a few ways. The primary way that it's troubled is it defines a planet as something going around the sun. This means that planets orbiting other stars, you have to call them exoplanets because they're not actually planets because they don't go around the sun, and that's just confusing nomenclature. Beyond that, our definition of a planet requires an object to be large enough that gravity squishes it to be round. We have lots of asteroids that are kind of dog bone shaped, teardrop shaped, mostly dog bone shaped, potato shaped. And all of these different potatoes and dog bones out there, they have so little mass that gravity doesn't try and flatten the bulges and dog bony bits of their surface. Now, if any of you have ever tried to build a sand castle, you know gravity likes to pull things down and not let you build too tall a structure. It's the same forces that flatten your sandcastle that also, flatten mountains on different worlds, causing Mount Everest to be about as tall a mountain as you can get with the gravity on Earth, while Mount Olympus towers significantly higher on the more diminutive Mars. And to those of you saying, but wait, I thought Mauna Kea was the biggest mountain. That's biggest mountain relative to its base, which is under the ocean. Everest is the biggest relative to sea level. Anyways, whichever way you tend to measure things, they can only get so big before gravity pulls them down, because our planet has its position, has its shape maintained by gravity. So does Ceres, so does Pluto, so do many of the moons of Saturn and Jupiter and our own Earth's moon. Phobos and Deimos in their orbit around Mars are allowed to be potato-shaped because they don't have enough mass to shrink them down. Now, with all of these objects that are round, why aren't they planets? Well, this comes down to the final part of the 2006 voted upon definition of planet, which says that a planet has to have cleared out its orbit around the sun. This is a particularly troubling part of the definition, because if you took the Earth, put it out in the orbit of Jupiter, its sphere of influence isn't big enough to clean out an orbit that big. So our own planet, if it were in a bigger orbit, would not count as a planet. There also isn't any geology in this particular definition. This means that a lot of people who study planets as geologically active objects really want to get some more science into this definition. Now, if we instead say that a planet is something that doesn't orbit another planet, so Titan can't be a planet, that instead orbits a star, that it has to meet certain geological definitions, and be round. That kind of a definition would get Ceres back, would get Pluto back, would start to add a lot of our dwarf planets in to what is defined as a planet. Now, as I said, that I know of, we're not voting on that this year at the International Astronomical Union. These kinds of definitions are worked on every 3 years when the International Astronomical Union meets. I was not yet a member when Pluto was demoted, so you can't blame me. But hopefully next time I will bring you there. I will be there to bring you all the details and to raise my hand and vote. So looking to see what else we have in the questions. So I'm not seeing. Okay, so I see Larry is saying about 20 astronomical units. Is that the furthest an exoplanet from a parent star has been discovered? So this starts to get down to the confusion of all the different ways that we find planets. And so here we are in this weird situation where we are finding planets using the dimming of their light as they pass in front of their parent star. And this only allows us to find stars that are very close, allows us to find planets that are very close into their star. The way to think about this, and here I'm going to use the head of Marvin the Martian. There we go. The head of Marvin the Martian as a planet. And I need a star. Here we go. So here is my star. Now, if Marvin the Martian is close up, he blocks a fairly significant, or at least his head blocks a fairly significant amount of light as he goes past. Now, if I get Marvin the Martian significantly further out, he first of all has a lower probability of actually passing in front of the star, and further out he's going to, well, he's getting closer to the camera. If he was not getting closer to the camera, he would block out less and less of the star at the greater distance. This means that by looking for eclipsing planets, transiting planets, like we do with the Kepler mission, we're only going to detect planets that are close in. Similarly, with the spectral way of looking for them, like is being done down on the Subaru telescope with their new pulsed laser spectrograph, in those particular situations, we're super sensitive to planets that are close in and have a smaller distance for gravity to work over, which means you can have a smaller world exert more force pulling a star around. So using those two different methods, we're only detecting things that are fairly close in. Now, the trick is, as we start to use other techniques, such as is being used with the Atacama Large Millimeter Array, where we're looking for deformations in the disk of dust and gas around young forming stars, that allows us to see things further out. As we're starting to use the VLT's infrared images to directly image planets, that is giving us a chance to see things further out. Now, we have begun with the Atacama Large Millimeter Array to see swirls and eddies in the dust around planets, around stars, that seems to indicate there are planets in the process of forming 80 to 100 kilometers out. Now, that's not to say that's where they're going to stay. That's just to say that is where we're seeing them now. So Larry, the furthest distance out that a planet has been seen, thank you for the follow, Rose and Michael 123. It turns out the distance that something is to be discovered depends on what technique you use. And I can't tell you specifically what the greatest distance is, because I'm pretty sure it's changing weekly. So looking to see what else is being discovered. Rose and Michael ask, where is it located? But I'm not sure what you're asking. No, you don't have to be a genius to learn astronomy, Rose and Michael. I am far from a genius. I just have a really good memory. Exoplanets are kind of found in all directions. So in today's episode, we looked at a baby gas giant in the process of forming, and I'm looking to see where the star is on the sky. I'm not sure it actually told me. Oh, there it is. I found it. So the baby gas giant that we looked at today shows us, shown to us in this image. This particular new gas giant that was just discovered around a red dwarf star is located in the constellation Centaurus. The dwarf star is named PDS 70. So you can theoretically go out and start looking for this object. Now, unfortunately, it is something that you're going to need probably a 8 to 10 meter telescope to see. So Centaurus is where this is located. So there are structures on the moon. They were left there by the Apollo astronauts. I feel like that was a trick question. I love the fact that we have man-made structures left all over the moon, whether it be the lunar landers that were left behind, the surveyor and lunar probes that crawled across the surface. We have littered our solar system with robots, and the moon is one particularly robot-covered world. It's not quite up there with Mars, not yet. They could have cleaned up before they left, but the truth is they didn't have enough fuel to bring back their garbage. We've learned more since then. So Hanny is asking, do we have a lot of red dwarf stars nearby? I heard they're usually hard to see. Getting at the nearby has been a bit of a challenge. We are able to photometrically find red dwarf stars by studying the sky with things like this. Was something the WISE mission did. Thank you, MMA Fighter, for the follow. So infrared telescopes will survey across the sky looking for small, faint red stars that have colors characteristic of red dwarfs. Now, the problem is that isn't enough information to figure out where those stars are located. At one point, I heard a speaker mention that our sun could be part of a binary system with an extraordinarily distant companion, and we might not actually have identified that companion because we haven't been watching long enough to see the star move with the quality of instruments we had at that time. Now, this is all changing. We have the Gaia mission, which is mapping out very carefully the motions both in the plane of the sky and spectroscopically radially in and out from us. And this allows us to say, hey, based on its motion, these stars are really close and these others are really far away. Here we are looking out and observing the sphere of space around us from our little spherical planet. And by combining data taken from all different distances from the sun, we are able to measure the three-dimensional movement of nearby stars and say just how nearby they actually are. So Hanny is asking, has anyone noticed odd motions of the sun to indicate it is in a binary pair? Since the sun dominates our own motion, we're essentially latched onto it, and I'm not sure we would be able to see the kinds of fine motions that would be indicated by an extraordinarily distant object. Just not sure. So Fenrig is saying, I've seen images of telescopes using powerful lasers to project artificial stars to correct for atmospheric distortions, but I don't understand how that works mechanically. Let me see if I can pull up an image of this. VLT artificial star. What you have, and these are amazing to see on a dusty evening. You can't generally see lasers, but dusty evenings allow it to happen. Let me switch views for just a second, and I'll do what I can to bring you a video of this from the European Southern Observatory. Pardon me while I figure out how to get this to work. Oh, it doesn't want to let me do it. Okay, so I'm going to have to show this to you at a lower size than I would like, potentially. There we go. I figured out how to embiggen it. Something very weird just occurred. Okay, hold on. This is what happens with live Hangouts. Sometimes you don't have the luck you wish for. Oh, their video is only 8 seconds long. Never mind. I'm not going to show you an 8-second long YouTube video because that will go poorly for everyone. So the way this works is you have your telescope, and next to your telescope is a giant laser, not on the head of a shark. And this giant laser shoots a beam that is precisely designed to excite often oxygen atoms in the upper atmosphere. And the only place that these atoms get excited is within the circular beam of the laser. So you fire a laser that is at an energy designed to excite atoms in the upper atmosphere. When these atoms get excited, they create a perfectly circular, glowy place because the excited atoms have electrons that jump to a higher energy level, don't stay there, and when they cascade back down to a lower energy level, they emit light. This perfectly circular place in the sky that gets excited, its light, as it travels back towards the observatory, has to travel through, well, all the intervening stuff and things, whether it be thermal layers or whatever, in the lower atmosphere. And it is these thermal differences, it is turbulence created by the jet stream, it is all these different things that cause that artificial star's light, that excited circle of atoms light, to get made not circular. There is a camera that very quickly is measuring the lack of circular in that excited artificial star, and then morphs the mirror of the telescope to make the not observed as circular light appear circular, because that is indeed the shape the light should be entering the atmosphere as. I'm glad to hear you're not a flat earther, Rose and Michael. I very much believe our planet is an oblate sphere, which is also just a fun set of words to say together. Looking to see what the comments are. So high speeds RAC is asking, how do they determine what kind of molecules are in the plumes coming out of, well, icy moons like Enceladus? With Enceladus, we got super lucky. Oh, thank you, Fenring. With Enceladus, we got super lucky. The Cassini space probe had on board mass spectrometers. This is the same kind of instrument that crime labs use to figure out what are all of the different molecules and atoms in some sort of a sample. So you take a weird unknown chemical, throw it in, and the mass spectrometer applies electric and magnetic fields. Thanks for the subscription, Fenring. And these different fields accelerate atoms of different masses in different ways, causing them to impact in different places on a detector. So you have one set of atoms hitting one place, you know exactly how many of that atom you have. You have another kind of molecule that impacts a different place, you now know exactly how many of that atom you have. Well, just like crime labs have mass spectrometers, Cassini also has a mass spectrometer, or it did before it plunged into the surface of Saturn. And its mass spectrometer was able to directly measure the content in a sample that Cassini picked up from the vapor from one of the icy plumes. So as Cassini flew past the moon Enceladus, its geysers happened to have sent a bunch of, well, water and ices and materials out into the nearby space. Cassini swooped in, scooped up some of this material, and in its own form of Crime Lab's investigation, measured exactly what the content is in order to figure out what is hidden beneath the surface on Enceladus. So we can sometimes tell what are the contents of a rock, a plume, something, just by looking at it. And this is done by looking to see what colors of light are reflected off of a surface. This only gives us, well, a surface understanding. To get the richer atom by atom understanding that we really want, this is where we need the samples. We often send robots to other worlds to make these samples for us. Little Curiosity is out there doing this on Mars. We often hope that we can scoop things out of atmospheres. MAVEN, as it orbits Mars, is doing this. The GRAIL mission going around the moon was able to do similar things with the lunar atmosphere. The moon does have a very diffuse atmosphere. And Cassini hoped to scoop up bits of Saturn's atmosphere and actually also gave us a taste, quite literally, of what's inside Enceladus. Okay, so was that enough puns for you? So we've been going for almost an hour today, which is okay because there was no one here to follow this episode up. High Speed, I'm glad that you were able to join us. And to all the new people out there watching, thank you for being here. Oh, Keeper of Maps, I don't remember what the composition of the moon's atmosphere is. I know that part of its composition is driven by the moon getting hit by things and particles lifting up off the surface. So I'm not sure what you mean by Mercury is so boring to explore, DPI. The Messenger mission went and sent us back amazing data from Mercury. And I can tell you this data is just as amazingly interesting as the data that we have from Mars, from the moon. And the frustration is, it turns out most people don't care. If you want to show Mercury some love, go to CosmoQuest.org. Help us map out this little world. It turns out that Mars in general gets the most attention, which is fine. We have an active science team desperately waiting on Mars data. The moon gets mentioned the most, so people keep returning to the moon. But Mercury is kind of the world that everyone forgot. So show Mercury some love. Now, if you're mentioning how we haven't really sent that many spacecraft to Mercury, this is because it's just super difficult to get a spacecraft in orbit around Mercury. I think that we're about to put our second orbiter into orbit with Beposax, but it may already be there. I may have things out of order. Peter, we don't so much have teams getting ready for manned missions to Mars as we have scientists, exploring Mars for all of its scientific wealth. Oh, Larry, that's awesome that you earned your Mad Mapper badge. Others, go be Larry. Go earn your Mapper's badge. That's awesome. So looking to see if there's any other questions. I'm mixed. Mars weather is actually, on average, colder than Earth because Mars is further away from the sun. Now, the reason I say on average is both of our worlds have place-to-place variations. Where I am right now in southern Illinois, it's in the mid-30s if you believe in Celsius. It's in the 90s if you believe in Fahrenheit. Whichever temperature type you like to use, I'm not converting to Kelvin. It is hot and miserable outside. But if I dashed down to New Zealand, it's quite cold. So place to place, our planet has a vast variation. And there are places on Earth that are currently colder than places on Mars. But most of the places on Earth are warmer than most of the places, if not all the places on Mars. I will never forget that the day that Little Opportunity landed on Mars back in 2000, I think it was 2005, may have been 2004, it was warmer on Mars than where I was located in the city of Boston. So on average, Mars is colder, Earth is warmer. Your individual results may vary. It's not going to be an all. It's not the first hour long. We've had a couple others, but today the conversation is going well, so I just kept things going, and no one is waiting to take over the channel from me. So Larry, you're gonna have to help us map out Vesta if you want us to get to Ceres. So thank you everyone for being here. Once again, as it says over my head, this is the daily space. We are part of CosmoQuest, and CosmoQuest invites you to join us at cosmoquest.org and help us map out our solar system. We have projects that are looking to define where are the safe places to land and where are the scientifically interesting places to explore on the Moon, Mars, Mercury, Vesta, and even, well, not so much the places to land, but the scientifically interesting places to explore right here on our own planet Earth. Check it all out and become part of discovering our universe. If you like what you see today, please give us a follow. We offer the daily space Monday through Friday, except on holidays. I probably will be here for the 4th of July anyways. Oh, Larry, you might have finished Vesta. That's entirely possible. If you like what you see, tune in Monday through Friday at 1 p.m. Eastern, 10 a.m. Pacific, 6 p.m. London. And I or another member of our team will be bringing you a quick roundup of our space news. The next program I believe will be appearing on this channel that is scheduled is tomorrow's Daily Space. Now that isn't to say there won't be random interrupting feeds. So like I said, give us a follow. Follows are free. This show is sustained through your subscriptions, and every bit really matters. We are part of the Astronomical Society of the Pacific, working in collaboration with the Planetary Science Institute and Youngstown State University. Thank you for being here, and remember, wherever you are in the world, have a fabulous morning, evening, or afternoon, and go outside and look up. Bye-bye.